Hello. We have successfully discussed about one of the seminal concepts in thermodynamics, namely the thermodynamic potentials. And by now you are all familiar with the four main thermodynamic potentials of use. And during the discussion of these potential functions, I have been telling you repeatedly that the enthalpy can be obtained mathematically from internal energy by the method of Legendre transformations. Moreover, the Legendre transformation of internal energy can also give the Helmholtz free energy, or from enthalpy by a proper Legendre transformation you can even reach the Gibbs free energy. So we have seen that Legendre transformations are helping us to move from one mathematical function to another mathematical function, which are all equivalent. And this session I'm planning to give you an outline on the mathematical technique, so that whenever you write a new equation in terms of this technique, you understand what actually you are doing. Because as I already have mentioned, it's always good that you have a clear knowledge of what physical things are behind every equation, or why certain mathematical operations are done in order to get newer and newer functions. Moreover, a knowledge of Legendre transformation as a mathematical technique will be helping you to understand many other topics that you will come across in your postgraduate courses, especially when you deal with the classical mechanics courses in your post-graduation MSc classes, as well as when you study about the statistical mechanics, there also you will be again coming across Legendre transformations. Now, in general, transformation are meant to simplify the solution of a mathematical problem. You are already familiar with some transformations in mathematics. For example, you have learned to convert the Cartesian system of coordinates into the equivalent spherical polar coordinates, or from Cartesian coordinate system you can move on to the cylindrical polar coordinate system. I hope that in the discussion of your electrodynamics, whenever you discuss about the electric field created by certain charge distributions, for example, if you want to describe the electric field created by a point charge, it's better that you shift over to the spherical polar coordinate system than to continue using the Cartesian coordinate system. The reason is well and clear, because the system that we are discussing, that is the electric field due to point charge, is having a spherical symmetry. You know, radially at any distance r from the point charge, the magnitude of electric field intensity will be the same along any direction in space. So it's better that we shift all our equations to spherical polar coordinate system to match with the symmetry of our system. Hence, what kind of a coordinate system that you have to use in a particular problem is decided by the convenience. Which coordinate system will make the solution of the problem easier? So that search will finally help you to decide which is the type of transformation to be used. Now, another example, if you want to find out the electric field distribution due to a line charge, you know, the field distribution due to a line charge is having a cylindrical symmetry with the line charge as the axis of the cylinder. So better than using the Cartesian coordinate system or using the spherical polar coordinate system, it will be always better that you depend on the cylindrical polar coordinate system. Hence, it's a matter of convenience once again. So in general, this is what always you have to understand. Whenever you are using the technique of some kind of transformations in physics or any topic, you understand the basic concept, the basic aim behind the process is to simplify the problem into a simple method. Now, so that is one thing about the coordinate transformations. Under transformations, you are familiar. Hope you remember, you learned about what is known as what you call Laplace Transforms, right? Okay, so in your mathematics complementary classes, I think by the time you are very familiar about what is known as a Laplace transformation. You know, Laplace transformation method helps you to solve differential equations in a better manner, in a convenient or in a simpler manner. So Laplace transform is also another example for mathematical transformations. There are several such transformations in mathematics, and most of these transformations will find applications whenever we are solving some problems in physics. So that is one reason why you are taught about different types of transformations in your complementary courses, which will help you to understand the say which kind of transformation will be useful in solving your physical problem. So this is your toolbox actually. This is like a mechanic. A mechanic should have a comprehensive toolbox, so that depending on the problem that you are facing, you should be able to identify that, yeah, I have a particular tool which can help us to solve this problem. Okay, so like mechanic is having different kinds of tools in his toolbox. All mathematical tools like transformations, differentiation, integration, addition, subtraction, whatever mathematical operations are just like mathematical tools, in the hands of a physicist. So it's up to the physicist to decide which tool will be the most suitable one in order to solve one particular physical problem whenever it arises. And Legendre transformation is one such mathematical tool. And especially this tool is useful when you have to shift the dependence of one function into some new variables. Means it's a mathematical technique used to obtain new functions, which are equivalent to the parent function. New but equivalent function. What is meant by equivalent function? Means whatever information was available in the original function will be available in the new function also. That is the meaning of equivalent function. But the two functions that we are defining by Legendre transformation will be finding its application in different context, different situations. Okay, and so they are equivalent functions from the existing functions by a change of basis. Basis means some variables. So let me just take the example that we have already done. So some of the example was like this. See, is it not? So what we have, you introduced the internal energy as a potential function, right? And we have defined that internal energy can be represented as a function of the volume of the system as well as the entropy of the system, and we named V and S as the natural variables of internal energy. Now you know that this internal energy is a convenient thermodynamic potential for situations involving change in volume and change in entropy, right? So if there is a situation where instead of volume, pressure is changing, the pressure is changing, or pressure is the control variable there. Now it's better that I do not depend upon you, but I need to define a new function which can be conveniently used in those contexts. So we have defined the second thermodynamic potential, namely the enthalpy. So H and we have seen the natural variables of h was defined as p and s. So how to go from one function to the other function, that depends on our requirement. So depending on our requirement, under what conditions I have to get the information regarding the system, we have the freedom to define newer and newer functions, and people have already defined it, so we depend on what is already defined, right? So this is what we have seen that. So just understand that V and S are what is known as the basis. V and S are known as natural variables, or otherwise known as the basis. So in this transformation, so this is a Legendre transformation, this is what I discussed. In this transformation, the variables or the basis is changed from Vs to Ps. So you can see here it's a multivariable. I can say that it's a two-variable function, right? Okay. So in this one, in this special transformation, one of the variable has been kept the same in the transformation. So S has been maintained as the same. So if I write it in general mathematical language, so let me make it in the language of mathematics. So I'm writing that I'm converting a function. Suppose you have a function of say x and y, f of xy. What I'm doing is that I'm converting this function f of xy into another related function, say g, right? G of, see that I'm writing g of some u, y. Did you note something? That I have maintained the y as the common basis or common variable in both the functions, right? So there is a relation between f and g. The information that is hidden in the function f will be also available with the function g, but in some other form, and we have to understand how it is obtained. Now you can't choose any you can't choose any desired function. There are some set rules, okay, if you have to get the information here. So we'll say that g can be regarded as the Legendre transformation of f, provided, so this condition is what is important. So it is a Legendre transformation. The condition is 1. The condition is that g is related to f by the equation f minus ux. If g is the Legendre transformation of f in this manner, then I can write g is equal to f minus ux. That is one thing you have to understand. And there is one more necessary condition. Okay, the second condition is that if you have to write it like this, then there should be a relation between this u, f and x. See that? What all things? U, f and x. There should be some relationship. And what is that relationship? U should be equal to dou f, or I can say df. Okay, so let me just take it. So dou f better, okay, dou f by dou x. You know why I'm preferring partial derivative, because f is a function of both x and y. So I'm taking partial derivative. So if u is a function, u is equal to the partial derivative of f with respect to x, then I can always relate, or I can always define the new function g as f minus ux. Now let me take some examples, or let me support this theory, okay, with some examples, okay, which already we have discussed. See here, can you see that this is the reason why I have written the equation for h. How do you write the equation for h? H is equal to, don't you remember the defining equation of h? H is equal to u minus PV, but we defined it as u plus PV. The reason is that u minus PV, actually that is the thing, okay, and why this negative sign you will understand. U minus PV, so finally it will become what? U plus PV, and that is the definition of h, right? Now how the other relation will be, okay? So if you have to write it like this, there should be a relationship. What is the relationship? That so you can just identify here what is u equal to. U will be equal to minus p here, right? and x is equal to, you can just see that this is x, this one is x, right? V is x, y is which one? S, and there is no role for y in our any of the equations, so I forget about this y. And what is u here? U is seemingly p, but actually u will be minus p. Okay, I will explain that one. So, and f is u. So what will be u equal to? So u equal to, I'm writing, let me write it, see, p equal to for the time being. So p equal to dou f by dou x. Dou f by dou x. So what is dou f? F is u. Dou u by x. What is x? X is what? V, right? X is V. You can see that the correspondence. So dou u by dou v. Dou u by dou v. Now, okay, keeping other things as constant, we'll see which one is kept as constant. So this is basically the thing. But do you remember, was our p equal to dou u by dou v, or was it equal to something else? So let me recall the equations. What was the equation that we had? We had the differential form of the first law, du equal to, it was minus p dv plus t ds. Hope you remember this one. Minus p dv plus t ds. It was d bar q. D bar q is written as t ds, right? So from this one, you can write what will be p equal to, p will be equal to, there is a negative sign here. Just remember this particular negative sign here. So that negative sign will tell you that p is equal to not what is that, dou u by dou v, but instead it is what? Minus dou u by dou v, or I can write this minus p is equal to dou u by dou v, both are things. That is why I told you that there is a minus sign here which is coming as what? Extra, and this has made it u plus what? Pv, right? So you can see that this relation between h and u you obtained by following this general mathematical procedure, right? Similarly, you can obtain all other transformations by this technique. You have to only remember this equation, and this is the condition, and this is the yet another condition. So you have to whether it will be a minus or a plus. For that, you have to check this particular thing. You have to check this one. If this equation is holding good, then you take it as positive. If it is not other way, you take the thing negative. Now, what actually we are doing? See. To understand it graphically, so I'm trying to draw a graph here. So you consider that you have some function. You have some function, because all what we deal here is regarding some sort of a function, right? So you have some function. So let me draw the function like this, something like this. So let me say that let the variation of the function, it's just something like this. I'm taking an arbitrary function. So let me say that this is what we write as f of xy. F of xy. Okay, so this is a function f of xy, right? And for example, in our case, f of xy is nothing but u, the internal energy, which is a function of v and s, right? Now, instead of the f of xy, f of xy has got some particular shape, right? Means it tells you how this function changes, depends on x and y, right? Whether it be a parabola or it be a straight line, all those depends upon the nature of the function f of xy. So there's a lot of information, mathematical information that is hidden there. Now, instead of depending on f of xy, I'm going to define another function, namely what? G of ui. Another function which is what? G of ui. How do we do that? Okay, for that what I'm doing is that I will be, see, at some point, say that this is the point. So at this particular point, I'm taking a point over here. So you can see that corresponding to this particular point, there will be certain value of x here on the x-axis. You take this is the origin, and there will be a corresponding value of y as well. Okay, so there is a y here, and that's the meaning xy, right? So there is a value here. Now the coordinates are x comma y. For this point, the coordinates are x comma y. That's what I mean. Some value of x and y, x1, y1, say. Now what I'm doing here is like I will be just drawing a tangent to the curve at the point. I'm trying to draw a tangent to the curve at this particular point. So let me say that I'm having a tangent at this particular point. Okay, so let me see. Let me say that this is a tangent. Okay, yeah. Just take it for granted that this is a tangent. Yeah. So this is a tangent. Now, this tangent has got a slope, right? This tangent has got a slope. So how do you okay, just represent the slope? You know, the slope is represented by what is known as tan theta, right? Slope is represented by tan theta, okay, at this particular point. So in order to do that, let me do one thing. Let me just draw it like this. Yeah, the same horizontal line, I'm just drawing it like this. If you want, you can just construct a very small triangle here. Or what I need is okay, I need at see, what is that, an angle here, right? I need an angle here. See, let me take it. See, this is the angle, right? This angle between these two straight lines. So that is my angle over here, right? See, it's not thick enough. Yeah, now it's there. So let me call that this is theta, right? The angle between this blue line and the green line, the two straight lines what I have drawn, this is theta. Now you know this theta will be equal to this theta as well, right? The thing, and this is 90 degree, of course, right? Now there is a y-intercept, the point where this slope line, the straight line is touching the y-axis. So this is a y-intercept. Now what I'm doing, I'm defining the y-intercept as g. The y-intercept is defined as g. Okay, for the time I'm just writing g, and see, let me find out what is the slope here. What is the slope? So you can see slope of the graph, slope at okay, sorry, slope of what? Slope of the function, right? What is a function? Slope of f of xy. That is a function. Slope of the function f of xy at x comma y, some particular value, x0, y0. What is that? How do you get it? That's given by tan theta at that point, right? That's a mathematics, simple trivial mathematics. So tan theta. So what will be tan theta equal to? I can write tan theta equal to see, just opposite side, right? This side divided by this particular side. And what is this side? What is this side? Okay, so let me write this g. Yeah, so tan theta is equal to yes, what is that? I can write it as like yes, dy by dx, is not? Okay, what it be? Dy by dx. So let me define it as u, right? So that is u, tan theta equal to u. I'm calling this slope as u. And what will be u equal to? U will be equal to dy by dx. And what is y? Y is okay, y. By y means we mean okay, what is that? F of x. So I can write it as df by dou f. Okay, instead of df, I'm writing it as dou f by dou x. Okay, dou f by dou x. So what is this one? That is u, and this u is equal to just I can write that's equal to dou f by dou x. Now see, let me also make the meaning out of this one. So this is equal to, there is further equal to u equal to, see, let me write, yeah, that's equal to tan theta equal to see, let me make this one something like this, g of u. For the time being, I'm writing it as g of u. Actually, I'm supposed to write g of u comma y. G of u comma y. I'm just simply writing as g of u. Okay, comma y you can presume because y is remaining constant. So g of u y, some reason I will tell you. Okay, so what will be this tan theta equal to? Opposite side. Opposite side will be equal to y minus, okay, y minus see g of uy, y minus g of uy divided by tan theta, no? Okay, divided by x, because that is this distance, no? Okay, that is x, right? So what you will get from here? What you will get from here? So here it is u on the left side. I have called the tan theta slope as u. So I will get ux is equal to right, y minus g of uy, y minus g of uy, right? But this okay, the y what I am writing here, I can say that that is like y is equal to f of x, right? Y is equal to, y is a function of, okay, x and y. So what I can do is that I can rewrite this one as this y is nothing but f of xy. Y is a function of Okay, is not just f of xy minus g of uy, minus g of uy, right? Or what will be g of uy? G of uy, that will be equal to, you just interchange it, that is equal to f of xy minus f of xy minus ux, f of xy minus ux, or g is equal to, simply if you forget about the brackets or the function dependence, g equal to f minus ux, because y is remaining constant, and this is the relation that we are getting. So g equal to f minus ux, which we have written here, g equal to f minus ux, right? Now see, what is the meaning of this equation? See, u equal to, see, this is the thing, u equal to dou f by dou x. See, I have used this f instead of y. I have used f instead of y. Actually, I could have written as dou y by dou x. You know, dou y by dou x or dy by dx represents a slope, right? So this y I have written as f of xy. That is why I have written dou f by dou x here. Okay, so you just think of that. If the slope of this straight line changes, you know that at different points on the curve, the straight line will be touching at different points on the y-axis, right? For example, if the point of our interest is here, so then you can see that this will be the you know, like this will be the tangent. So now you can see that the point has shifted out to here. Okay, so what will happen is that as you change the points one by one, if this is the point, then automatically you will have another okay, what is that, slope, another straight line to represent the slope. So maybe this is okay, or it can be even, that is not the thing. Okay, so let me just change it. So I will have to just shift it, right? So it's only a matter of thing. Then the y coordinate will, of course, it will, sorry, the y coordinate will be, yeah, so there is some, okay, yeah, the maybe, yes, okay, yeah, something like this, yeah, just okay, and you can just extend this one down, you will get a minus y intercept, of course. So you can see that as the point on the graph changes, there will be different value for g of y. There will be different values for g u of y. It means that the y-intercept, which I have taken as g, has got a clear dependence on the slope of the original function. So when the slope of the original function changes, actually the value of the function is also what? Changing, right? Okay, so corresponding to every point on the original function, there is a corresponding point on the y-axis. I repeat, corresponding to every point on the original function xy, every pair of point xy on the original function, there will be a corresponding value for the function g. So what does it mean? Whatever information is hidden in the original function can be obtained from the equivalent function g, where okay, g actually represents the y-intercept, the y-intercept of the slope, right? Y-intercept of the, I can say, the slope, which the slope is making on the y-axis, I can say. So the conclusion is like this: f and g can be equivalent function. Whatever information is hidden in the original function will be available in the new equivalent function obtained by Legendre transformation through the slope relationship. And that is one reason why we have been writing or using this relationship. So what you have to do in all our transformations is one, see whether it is satisfying this condition, and then if you can do that, confirm that, you can use any relation like this. So same thing you can repeat, and you can just try for the two more transformation we have discussed. That is transformation from u to a we have discussed, okay, and also from see h to g we have discussed. H to g we have discussed. Please take time yourself and try to see whether such a transformation can occur, like I have explained for the first transformation. I leave it as a task for you, because my basic aim was to understand that there are certain mathematical techniques which can help you to simplify your solution, so that it will be convenient to use in different context. Okay, and yeah, before I close, let me tell you about one more transformation that you will be doing, especially in your electrodynamics classes, what is known as a gauge transformation. I don't know whether it's already discussed in the present paper of electrodynamics. There is a gauge transformation that we'll be doing in electrodynamics classes. There are two kinds of gauge transformations you'll be doing. One is known as the Lorentz gauge, and the other one is known as the Coulomb gauge. Both are also transformation, mathematical technique to simplify the solution of what is known as Maxwell's equations. Okay, so when you learn that one, remember this is one special kind of transformation belong to the very broad family of mathematical transformations that is there to help us. Okay, thank you.